Okay, so this is an example of graphing polynomial functions. The first step to graphing polynomial functions is that we would need to factor to find the zeros, which are our x-intercepts on our graph. The nice thing is this function is already factored, so we just need to figure out which would make each of the factors, the expressions within each set of parentheses, equal to 0, because that would be what makes the entire equation equal to 0. When we multiply anything by 0, our answer would be 0. So let's go ahead and do that. The x minus 2, if we were to plug in x is equal to 2 there, would be an intercept. For the x minus 1, we'd plug in x is equal to 1, and then for the x plus 3, we'd plug in x is equal to negative 3. So those would be our three x-intercepts. We can go ahead and mark those right away on our graph. We have a dot here at x equals 1. We have a dot at x equals 2. It's hard to make dots on here. And then x is equal to negative 3 is our other x-intercept. Now, the nice thing about these points is that they're the critical points for our interval chart. So you can go ahead, draw on our number line like we're used to doing for our interval charts, and go ahead and plot the critical points on here in numerical order, just like you'd find them on the number line. So you have negative 3, and then further on up we'd have 1, and even further on up we'd have 2. And then just like when we've done interval charts in the past, we now want to choose x values in between all of these critical points. This is going to tell us the location of the graph in between each of the intervals of the x-intercepts. So let's go ahead and we will do negative 4 here. We will do 0 here. You should always do a y-intercept if possible. The only time it wouldn't be possible is if it already is an x-intercept and it goes through the origin. In between 1 and 2 we have 3 halves. That's the same thing as 1 1/2. And then here we can do 3. Now you can, sorry, I don't know why I keep hitting that. You can go ahead and obviously take your own time to plug these in and make sure you're following along, but I'm going to go ahead and give you what you end up getting when you plug these in. So you'd get negative 30. This is a negative value, which means everywhere to the left of negative 3, y is going to be a negative. In between negative 3 and 1, we're testing the point x is equal to 0. When we plug that in, we're going to get y is equal to 6. That's a positive point, so that means everywhere between negative 3 and 1, the graph will be above the x-axis. When we plug in 3 halves, we end up getting out a negative 9/8. This is a negative value, so it's going to be below the x-axis. And then to the right of 2 on our number line, if you plug in 3, for example, we're going to get out y is 12, which is positive, which means it's going to be above the number line everywhere to the right of positive 2. Now, the nice thing about these is they actually give us some points we can go ahead and plot. Some of them are obviously going to be off our graph, so we just want to draw the graph to generally go in that direction. But I see right away the y-intercept is 0, positive 6. 6 would be right here. And then at 3 halves, which is 1 1/2, we're going to be at negative 9/8, which is just below the negative 1. So right about there. And then we can go ahead and make the general shape. Except actually I need to make it steeper because we know right away at negative 4 it's going to be negative 30. And then going back up, it's also going to be pretty steep because we know at positive 3 it's going to be 12. So that's what our graph would look like. Double check that it has the correct number of turning points because n, the highest degree, was equal to 3. That means that there is at most 2 turning points. And we can see the 2 turning points in our graph. And then finally, just double check that end behavior because the leading coefficient was positive, it was actually 1x cubed. It should fall to the left and rise to the right, which our graph does, so that double checks.